Good morning, everybody. Welcome back to Abstract Algebra. Plan for today is we're going to do one last page in the quotient group packet, and then we're going to start our final packet on group theory. Yes. This will be a packet on fit, how to stay fit, or alternatively, the first isomorphism theorem. I've got my usual office hours on Monday, hour before class and 2 o'clock. And don't forget, homework 6 is due Wednesday. Now, this is a message out there mainly to those of you who are watching this remotely. Apologize for class on Wednesday. The video got cut off from the second half of the recording. In my other class I recorded, the audio got completely cut off instead. So, some weird stuff going on with the software there. But, I'm hoping I got it fixed. I reinstalled the camera software and got a new little connector thingy to connect the cable to my computer. And I'm hoping that fixes the issues. It seemed to work out in my morning class, my 105 that I recorded, so I'm hoping it works out for this one. But if it doesn't, we will figure it out together. So I apologize for that, those of you watching this remote. All right. Hey, Dr. G, got any jokes?
I don't have any jokes. I don't have my joke book. It's over there. Do you want to hear a joke I stole from Dr. Steele?
All right, let's hear it.
It's not actually funny. It's actually just a nice thing he said to us. How many Hillsdale students does it take to change a light bulb?
Too many.
If there's Hillsdale students in the room, it's already bright enough. I can't believe he said that.
Wow, I've never heard such a terrible joke in my life. All right. Four friends who have been doing really well in calculus decide to take a weekend road trip together instead of studying for the final. Not surprisingly, they drink too much, oversleep on the morning of the final, and get back to campus after the exam is already over. One of them concocts an explanation asked for the professor's mercy. Says, "We went to my parents' cabin for the weekend so we could have a quiet place to study. Driving back on Monday morning, we got a flat tire. Didn't have a spare and took hours for help to arrive. I'm so sorry." Professor says, "I understand. It's all right. Tell you what, if y'all come back tomorrow morning, I'll give you a makeup exam." So the next morning, Professor sits the 4 students in different corners of a large lecture hall. The tests are only 1 page long. They're already on the desk. Professor tells students to begin. On the front side of the paper is just one question involving a definite integral that all the students get easily. On the back side, there's just one question as well. Which tire? All right. So, plan for today is, I already talked about the plan today. Dr. Gershel, get your head in the game. So, last time we talked about normal subgroups and why we needed H as a normal subgroup of G in order for G mod H to actually form a well-defined group structure. One last theorem that I'd like to talk about from the previous packet on quotient groups before we move on to the new stuff. And that is a fun little theorem that says G is abelian if and only if G mod the center of G is cyclic. So in other words, we can actually determine whether a group is abelian or not by looking at the quotient group when we take a group G and mod out the quotient group by taking G mod its own center. Where again, the center of G is just the set of all elements in G that commute with everything else. So this is going to be an if and only if proof. So we need to prove 2 things. From left to right, that if G is abelian, then G mod the center is cyclic. And from right to left, that if G mod the center is cyclic, then G has to be abelian. Anybody have a preference for which way to go first? Okay.
Left to right.
Left to right. All right, that's the easy one. So, let's suppose G is abelian. If G is abelian, what can we say about the relationship between the center of G and G itself? If G is already abelian to start with.
Isn't the center of G equal to G then?
Yeah, exactly. G is its own center because G being abelian implies every element in G commutes with everything else. So the set of elements commute with everything else. is precisely equal to that group. So if G is equal to its own center, what can we say about G mod the center of G? In particular, how many cosets is the center of G going to have within the group G?
That's going to equal 1.
It's going to be 1, since the only coset of the center of G in G is, well, that coset is just that set itself. We only have a single coset, namely that, and what do we know about groups of order 1? In particular, what do we know that's going to be helpful to us in going from left to right here? Mark?
It's cyclic.
Yeah, it's cyclic. It's the trivial group, so it has to be generated by its only element. Thus, G mod Z of G is trivial, and it's cyclic. So that direction's pretty straightforward. If G is already abelian, then G mod its own center only consists of a single element, Z of G itself. Therefore, it's trivial group, and trivial group is cyclic because the one element will always be generated by itself. Any questions about the forward direction? The backward direction is a lot spicier, so let's try and prove that one. So let's suppose G mod the center of G is cyclic. And our goal is going to be to show that G is abelian. Well, since G mod the center of G is cyclic, that means it has to have a generator. Anybody have a name they would like to give to the generator? Angeline?
Little G.
Little G? You just want to call it little G?
Little G double hat.
Little G.
Sorry. Oh, he's mad.
Well, we know that all the elements in G mod Z of G are cosets, so let's just call it G, a little G Z of G. She's done with that. This is a haberdashery.
What is a haberdashery?
It's a hat store.
Are you serious?
Yeah.
That's sick.
It is.
Why does everyone like you to know that?
Yeah, why do you guys all know that?
I just knew it.
I wasn't that homeschooled.
So if G mod the center of G is cyclic, then there has to be a single coset that generates the whole quotient group. And Elena's chosen to call that coset little g times Z of G. She chose something else, but I made it much less foolish. So we know that it's equal to little g times the center for some little g in G. Now, we need to show that if we take any two elements in G, they're going to commute. So I'm going to let A and B be elements in G. Goal, show that AB equals BA. Well, I want to somehow rely on the fact that the center is cyclic and being generated by this little g times Z of G. So, what do we know about this? We know that A, if we take the coset of the center, where we multiply out in front everything by A, I claim that's going to be an element in G mod Z of G by definition. It's a coset of Z of G, so it has to be in the quotient group. But we know that the quotient group is being generated by this single element, little g times the center. And if A Z of G is an element of the group generated by little g times z of g. How does that tell us, or what does that tell us about the form that a z of g needs to take? In other words, in order for a z of g to be an element in this cyclic group, what does that mean we could write about a times z of g in relation to little g z of g?
It's a power of it.
Exactly. It's going to have to be gz of g to the n, which we could rewrite as just being little g to the n times z of g for some integer n. Whoa, Dr. Gerstle. Why does little g times z of g raised to the nth power give us the same thing as little g to the n times z of g? The reason is if we take g times z of g and multiply by itself over and over, it comes out due to the fact that when you multiply any two of these cosets, you're just taking the product of the two corresponding elements out in front and then multiplied by z of g. So that would give us a g squared z of g times a bunch of copies of g z of g, and then in the end, you would just end up with a g to the n out in front. It's just due to, in other words, the group operation for how the quotient group works. You multiply two of these cosets by just multiplying their corresponding elements out in front together. So we know that a times little z of g, or a times little z of g, little a times z of g has to be equal to little g to the n times z of g for some power n. And then we can say that we need a new piece of chalk. And once we have a new piece of chalk in hand, we can then say that since a itself has to be an element in a times z of g, because a is just equal to a times the identity, then the identity has to be an element in the center. Since a is an element in this set, g to the n times the center, what does that tell us about a way that we could write out a? In other words, what would an arbitrary element in this coset look like? If we're taking something in little g to the n times the center. In other words, what would an element in this set? What would be the general form of an element in this set? I should say. Right?
Is it g to the n?
Just g to the n. If a is in this coset, it has to just be g to the n.
Times z of g.
Times z of g. Well, keep in mind, a and g to the n are just going to be single elements in there. So I think we need to multiply by an arbitrary element within the center. So basically, a is going to be equal to g to the n times some x, where x is just going to be some element in the center. Because everything in this coset is just going to be of the form little g to the n times some element in the center of g. Just like, if it helps, you could think about like letting h be the center of g, and then just say, if b is an element in this set, that just means b has to be equal to ah for some little h. Same sort of thing here. In order for a to be an element of this coset, that means a has to be of the form element out in front times some element in the center. So we know now that a is equal to g to the n times some element x in the center of our group. Everyone okay so far? So we could say something similar. We could say something and say similarly, b is going to have to be equal to g to the ny for some integer m and for some element y in the center of g. And that's just by going through the exact same argument. You could say B z of g is an element in this group, so B z of g has to be g to the m z of g for some m, and then that means that since B is in B z of g, that means B has to be equal to g to the m times some element in the center. It's basically the exact same argument, shows that B can be written in a very similar way. Some power of the element g times some element y, get connected. Some element y that's contained within the center of our group. So now that we have those, we can start going to town and show that we have some commutativity in our group. Because our only goal, keep in mind, is to just show AB is equal to BA. But now we can have some fun and we can say, thus, A times B is going to be equal to g to the n x times g to the my. Just using our alternative forms of what we found for how to write A and B. And now we can play around with some stuff. I claim, so first of all, let's see. I'm going to use associativity to play around with the parentheses and get x times g to the m as a single term in the middle. I claim that's going to be equal to g to the m times x. And why do we know that x times g to the m is going to be equal to g to the m times x? Right?
Normal subgroup.
Because what is a what now? What's a normal subgroup? Well, G is the entire group. We don't know if, I mean, we could say G is a normal subgroup of itself, but I don't think that's what's going to allow this to happen here. I don't think the fact that x g to the m equals d to the mx is going to come from properties of normal subgroups here. I think it comes from something we know about one of these elements.
X is in the center.
We're using the fact that x is in the center of G, which means that x automatically has to commute with every element within the group, including g to the n. And from there, we can use some associativity. Separate this out into g to the n times g to the n times g to the n times g to the m times xy, which thing on the left is just going to be g to the n plus m. I'm going to do a switcheroo here and say that xy is equal to yx. So why does x times y have to be equal to y times x? Okay.
Because X is still in the center.
Because x is in the center. Or alternatively, if you prefer, because y is in the center. For either of those two reasons, xy would have to be equal to yx. They would both commute. I'm going to have a little bit of fun and give the opposite reason to the one you gave. Because y is in the center. And now I'm going to split up g to the n plus m and say that's just going to be g to the m times g to the n times yx. Because g to the n plus m is the same as g to the m plus n, so to speak. And now we can use some associativity and say this is just g to the m times g to the n times y times x, which in turn is going to equal g to the m times y g to the n times x. Why does g to the n times y have to equal y times g to the n? Yes, Peter?
Y is in the center.
Since y is in the center. Which, we do a little bit of associativity one last time. We'll get g to the m y times g to the n x, and bippity boppity boo. That's BA. And then g is the other. G is abelian because we've shown that A times B is equal to B times A for any two arbitrary elements, A and B. So, if we wanted to, we could have said AB is G to the n x times G to the m y, which is going to equal G to the m y times G to the n x, because all four of these elements commute with each other. X and Y are going to commute with everything in the group, by definition, because they're in the center. And G to the n and G to the m are going to commute with each other because they're just both powers of the same element. G to the n times G to the m versus G to the m times G to the n. They'll both multiply out to just give G to the m plus n. And so everything commutes with each other. Everything is awesome. AB is going to have to be equal to BA in the end. All right. Any questions or comments about this one? This one, by the way, is another fun little way to answer some of the questions on, what was it? Homework, I forget what number it was. The one where you were proving things about like G, the index of the center of G and G can't be prime. Like parts C and D, the fact that like G mod, Z of G has to have order less than or equal to 1/4 the order of G, could use this theorem to actually prove that fairly easily. Because if G is non-abelian, then G mod Z of G can't be cyclic. And if G mod Z of G can't be cyclic, then in particular, it can't have order 1, 2, or 3, and thus it has to have order at least 4, which means G has to have order at least 4 times the order of Z of G. Boom, I just did 3C from several homeworks ago. That would be an alternate way you could prove that, is to use this theorem. And I just think it's a little bit of a fun one, just because it gives you a little bit of practice playing around with cosets and such, and having some fun playing with elements in the center. All right, time for the first isomorphism theorem. I forget who it was. Elaine, I think you asked me like early on, like, is there an easy way to check if a group is a normal subgroup without having to go through and check all the left cosets versus all the right cosets? There is a much easier way to prove something as a normal subgroup. And it turns out you can prove something as a normal subgroup of G without necessarily having to rely on the normal definition of looking at left versus right cosets. You can prove something's normal by showing that it's the kernel of a group homomorphism. Let's write this out. So you can say that if H is a subgroup of G, H is going to be a normal subgroup of G if and only if H is equal to the kernel of phi for some group homomorphism, phi, a function that goes from G to some other group G prime. So, can somebody refresh my memory? What is the kernel of a homomorphism? What do we define to be the kernel of phi? If phi is a map from G to G prime, kernel of phi, we said, is what? This is something we talked about way back in the day when we were talking about homomorphisms and isomorphisms for the first time. What did it mean to take the kernel of the homomorphism? Glad I did this review question. It's going to be a subgroup automatically of the first group. And in particular, it's going to be a set of all elements in the first group such that if we threw it into the map phi, what would we end up with? Peter? Bingo. It's going to be the set of all things that happen to map to the identity of the second group. So what this is saying is that if H is a subgroup of G that happens to also be the kernel of some group homomorphism, then H automatically has to be a normal subgroup of G. And vice versa. if H is a normal subgroup of G, we can find a function phi from G to some other group for which H is the kernel. It's another if and only if. So as a quick example, let's say we have the function phi going from Z to Z mod NZ, where we take an integer and we're going to spit out the same integer mod, oh wait, I forgot, we have a new, there, we get that. I forgot we've talked about the new definition for Z mod NZ, where we're just looking at cosets. So let's say we take in an integer and we spit out an element in the quotient group Z mod NZ equal to X bar. So in other words, the coset of X within the quotient group Z mod NZ, that you could write out as just being X times NZ. What's going to be the kernel of this homomorphism? In other words, which elements within the integers, what's the subgroup of the integers, that if we were to plug in elements within this kernel would just spit out the identity element in Z mod NZ, meaning NZ itself? Or if I phrased it another way, what would be the set of integers that if we mod it out by n, we would just get something, we would just get 0 mod n? Nick?
K times n, where k is just an integer.
Okay, so just the set of all multiples of n, in other words, is going to be our kernel. The set of things that if you, is going to n, so, in other words, just nz for short. The set of all multiples of n. Because if you take something that's a multiple of n, and you mod out by n, so to speak, you're just going to get 0. And vice versa. If you have something that when you mod out by n gives you 0, it has to be a multiple of n itself to begin with. So what this theorem right here tells us is that nz is the kernel of a homomorphism from the integers to some other group. That immediately then is going to tell us by our theorem here that that nz has to be a normal subgroup of the integers. It's a normal subgroup because it's equal to the kernel of some homomorphism from the integers to some other group. But Dr. Gerstel, aren't the integers in abelian group, so we already knew NZ had to be normal because every subgroup of an abelian group is normal? Yeah. But it's still kind of a nice, fairly straightforward example of, I think, one way you can show that a group is a normal that H is a normal subgroup of G is to just find a homomorphism from G to some other group for which H is going to be the kernel. In other words, find some homomorphism from G to another group where H is precisely the set of things that get mapped to the identity in the second group. If you can do that, great, H is a normal subgroup of G. If you can't do that, H is not going to be a normal subgroup of G. Any questions about this example here or the statement of the theorem before we jump into our proof? Let's do it then. So we're going to prove that assuming you're starting off with some subgroup, it's going to be a normal subgroup if and only if it's the kernel. So let's just start off. We're going to suppose H is a subgroup of B. Steph, what's taking on you for these sorts of questions? Would you rather go from left to right first or right to left? Because we have an if and only if. Left to right. Okay. So in other words, Steph wants to start by assuming H is a normal subgroup of G, and then showing H would then have to be the kernel of some homomorphism. That is not the right packet. Where's my notes on this one? Here we go. So, going from left to right, we're going to suppose that H is a normal subgroup of G, and we'd like to find some homomorphism from G to some other group for which H is going to be the kernel. So I'm going to define a map Phi that's going to start in G, and it's going to go to another group, and the group I'm going to choose is G mod H. H is a normal subgroup, so G mod H has to form a group. So theoretically, we could hopefully form a homomorphism from G to this other group, G mod H. And I'm going to define it by taking an element little g in G. What do you think I should map little g to? We want to define our function that starts with elements in G and ends up with elements in G mod H, which you may remember as just being the set of all cosets of H and G. What would be a map that would take little g to some elements in this group and do it in a way such that H is going to be the kernel of this map? So in other words, only elements in H are going to map to the identity of this group. What would be a coset that we could map a little g to? Okay.
GH.
Little g times H? Is that what you propose? Let's give it a whirl. So Nick proposes that if we define our map Phi in this way, we're going to A, get a group homomorphism, and B, H is going to be the kernel of that group homomorphism. So let's see if we can show that. So, first of all, I'm going to try and prove that's a homomorphism. So for all little g1 and all little g2 in our group G, we take phi of g1 times g2, we should get the same thing as phi of g1 times phi of g2, if this is a homomorphism. Well, by definition, phi of g1 g2 is just going to give us g1 g2 times h, that coset, which lo and behold is going to be g1h times g2h, because that's how our group operation in G mod h works, is that little g1 times h times little g2 times h should give us the same thing as little g1 g2 times h, which is in fact going to be phi of g1, phi of g2, hence phi is a group homomorphism. Neato mosquito. What else do we still need to show in order to finish our forward direction? We've proven that we've defined a map phi from G to G mod H that gives us a group homomorphism. What do we need to show if we want to prove the forward direction still of our proof? Okay.
That it's the kernel?
We also need to show that H is the kernel of this map. So I claim this does work, that the kernel phi equals H, since first of all, the identity element in G mod H is just going to be what?
I do not know.
I don't know what the identity element is in the quotient.
No, I quotient groups.
Quotient groups are scary. I don't blame you. Just give me H. And I would say phi of G, which by definition is this thing, will be equal to H if and only if G is an element in H to start with. So in other words, the set of all elements in the group G that map to the identity in G mod H, which remember, the identity in G mod H is just H itself. The set of things that are going to map to H under this map is just going to be, well, it's just going to be the set of little g that happen to lie in H to begin with, which is just going to be the subgroup H. So we know that phi is a homomorphism from G to another group for which H is the kernel. And I think that'll do it. That should give us our 4 directions. Nice choice of homomorphism then. Any questions or comments about this direction? Yeah, okay.
When are we allowed to like do stuff like that with like the whole group without like taking out like a tinier arbitrary element of it?
When are we allowed to do stuff like what now? Sorry.
I don't know. I remember like.
Oh, when do we have to check that our group operation is well defined? Is that your question?
Maybe. I remember there was one homework that like I was using big H and I was multiplying things by it and you're like, you can't do that. But I don't remember why.
I don't either.
Okay, cool. All right. Well,
I was gonna say, why don't you take a look at your homework later and maybe this could be like an office hour question or something.
Sounds good.
I don't remember offhand what the context was you're talking about. Sorry.
That's all right.
Any other questions? So we've shown that if H is a normal subgroup of G, then H has to be the kernel of some group homomorphism. We'd like to be able to do the other way around and show that if H is the kernel of some homomorphism, then H also has to be a normal subgroup. See if we can prove that. But first, okay, good, the video's still working. Hopefully the audio is too. Hello, can you hear me? Hello. Oh, shouldn't have erased that. If H is G, H is a normal subgroup, if and only H for some group homomorphism phi from. Okay, so let's prove the backwards direction now. So now we're going to suppose that H is a subgroup of G, and H is equal to the kernel of some function phi for some phi going from G to another group G prime, a group homomorphism. And our goal is going to be to show that H is a normal subgroup of G. So what I'm going to do is I'm going to take an arbitrary element, little g, in our group G, and little h, an arbitrary element in our group H. And for whatever reason, I want to look at this thing. I'm going to look at phi of little g, little h, little g inverse. And what I want to do is I want to show that little g, little h, little g inverse is in the kernel. Hence has to be in H. Let's see if we can prove that. Well, we can use the fact that phi is a group homomorphism to say that phi of GHG inverse is going to be phi of G, phi of H, phi of G inverse. So here, this is relying on the fact that phi is a homomorphism. I claim we know exactly what one of those three things is going to be. I claim we know exactly what this thing is going to be. What should phi of little h be equal to if little h is an element in big H, and if big H is the kernel of our group homomorphism? Big H is the kernel, and little h is an element of big H. What is that going to tell us that phi of little h would have to map to? All right?
The identity element in group 2?
The identity element in the group 2. Bingo. So that's going to map to the identity element in G prime, which we're we're going to end up with phi of g times the identity in G prime times phi of G inverse. Well, the identity element in G prime is not going to affect our product here, so we can just kind of ignore it. So we'll get phi of G times phi of G quantity inverse. And what's that going to be equal to? If we were to take phi of G times the inverse of phi of G.
Isn't it the phi of the identity element of the first group?
Yes. What is phi of the identity element in the first group? Well, if we have a group homomorphism, where does the group homomorphism always map the identity of the first group to? Which element in the second group?
Identity.
Yeah, it's going to map it to the identity of the second group. Which here, if we just take phi of G times the inverse of phi of G, by definition, thing times inverse of thing is always just going to be the identity element of that group. So it turns out that phi of little g, little h, little g inverse is going to be equal to the identity of the second group. So thus, phi of little g, little h, little g inverse is going to be the identity element in the second group, G prime. So where does that tell us that little g, little h, little g inverse has to be an element of, if it's getting mapped to the identity element in the second group? Elaine?
The kernel of phi or h.
Bingo. By definition, if GHG inverse gets mapped to the identity in the second group under phi, then little g, little h, little g inverse has to be an element of the kernel of phi. And as we assumed from the get-go, the kernel of phi is just h. That tells us little g, little h, little g inverse is an element in h. Which in turn is going to tell us this set right here, little g, big H times little g inverse. We've just shown every element in this set has to be an element in H, which tells us this set is a subgroup of a subset of H. And here's the kicker: if this set is a subgroup, or I said it again. If this set is a subset of H, we had a nice theorem from the last packet that said this tells us something about H. What does it tell us about H? If little g, if big H, little g inverse is always a subset of H. That was equivalent in the last, we proved it in the last packet, that was logically equivalent to Dave.
I mean, it's abelian? No.
Not necessarily abelian.
Didn't we say like two cosets either have everything in common or nothing in common? So if it's a subset, then they're equal?
Yeah, but we did say something like that once upon a time. However, these are not both cosets of H because, not unless you want to get to something I haven't defined, which is a bicoset, which is where we have a coset on the left and the right at the same time. You really want to do that, Nick?
Never mind.
I thought so.
Isn't the theorem that means H is a normal subdivision?
Bingo. Theorem is technically, this is true if and only if H is a normal subgroup of E. But yeah. So in other words, if H is the kernel of a group homomorphism, H then has to be a normal subgroup of G. So now we have proved our if and only if statement. A subgroup is normal if and only if it's the kernel of some group homomorphism. What do y'all think? Think the first isomorphism theorem is a pretty fun one? CT nods. Yo, you don't know that. That's not the first isomorphism theorem. It's let's flip the page and we're going to talk now about the actual first isomorphism theorem. So this is actually, I think, a pretty cool result, but we mainly care about it, and it is a nice way to tell when do you have a normal subgroup. You can show you have a normal subgroup if you can find some homomorphism for which it's the kernel. But the first isomorphism theorem is something that is going to rely on this result, not just this result itself. And basically, it's going to tell us, I'll give you the shorthand version first. It's going to say that it's basically going to say that if you take a group G, you mod out by the kernel of a group homomorphism, that's going to be isomorphic to the image of your group homomorphism. That's what the first isomorphism theorem says. That anytime you have a homomorphism from one group to another, if you take the original group and mod out by the kernel of that phi, you're going to get something that is isomorphic to the image of that phi. And you may not think so from looking at it, but this theorem, this result right here, is arguably the most important result we'll have talked about so far this semester, in terms of how much in group theory and abstract algebra in general it's going to give us. Result that says, take a group, mod out by the kernel of a homomorphism, that's going to give you something that's isomorphic, meaning mathematically the same as the image of that homomorphism. Should all be in shock and awe right now. For any group homomorphism, phi from G to some other. I guess in the packet I wrote this out as phi of G. Same thing either way. Remember, the image of a homomorphism is just the range of our function, the set of all things that actually get mapped to by some element in the first group. The set of all, let's say, A and G prime, such that A is equal to little phi of G for some G, an element in our first group. And so the set of all, basically the range of our group homomorphism is always going to be isomorphic to the original group modded out by the kernel. And that's where we're going to cut things off for today. So when we come back on Monday, we are going to prove the first isomorphism theorem. And spoiler alert, remember that well-defined issue of quotient groups that we had back last class that was causing us some grief? That's going to be making its return in our proof. You all have a good day. Hope my recording got the audio and video for the whole thing. Looks like it got video. And I will see you all on Monday.